It's been a pleasure to be at this really fantastic conference. I would like to thank the organizers for putting it together and giving me the chance to speak at it. So I'm going to give an update on some of the work that my group has been doing over the past year and a half or two, thinking about how to generate new forms of electronic crystallization that can also trigger topological phases and how these types of things interplay. So first and foremost, let me just acknowledge and thank the people who did this work. So it was primarily done by my postdoc, Jason Waters, who actually just left for his faculty position at University of Denver, PhD student Anna Okinkova, and then some early development from another PhD student, Ellis Thompson. A lot of this work was done in collaboration with Josh Folt's group at the University of British Columbia. So the measurements I'll show you are kind of a mixture of measurements taken in Dilfridge's in my lab, and then Dilfridge's in Josh's lab, and it's really been an extremely valuable collaboration. And in his lab, the work was done by an undergraduate, Ray Su, who's really an absolute superstar. And then our theory collaborator, Yahui Zhang, who you heard from earlier in this conference, and his student, Boran Zhao, and internal collaborations with Zhaodong and his group and Bien from the Japanese growers. Okay, so I'll keep the introduction short by now, since I'm sure you're sick of hearing about Hall crystals. But I think the general idea of what we're doing now is to start with the Moiré lattice, which, in the right combination of materials and twist angles, gives us a combination of flat electronic bands that can host strong interactions and non-trivial quantum geometry, so basically Berry curvature within these bands that can lead to topologically non-trivial phases. The strong correlations can lead to Stoner instabilities that can polarize spin or Valley degrees of freedom and lead to different forms of orbital or spin magnets in these materials. And then on top of this, interactions can further, say, crystallize the electrons, form charge density waves, or they can preserve all of the remaining symmetries of the system and instead fractionalize the electrons, which, as we know by now, can lead to the observation of the fractional quantum anomalous Hall effect. And I think an interesting question now is how these two different types of topological orders can interplay with one another. Do they strictly compete? Or are there scenarios where they can coexist? And just generally, I think these are open questions in the field.
May I ask you a question? I just want to make sure that when you say crystal, I have nothing against crystal, but you don't have any direct experiment evidence that's a crystal.
No, it's inferred.
Inferred and the theory inspired.
That's right. So let me show you what we see, and then you can ask me again. Yeah. Okay, so, we've heard by now the two different systems, twisted MOTE2 and rhombohedral pentalayer graphene with a moire from boron nitride, that can generate the zero field fractional Chern insulators, leading to the observation of the fractional quantum anomalous Hall effect. I think less focused on so far has been other recent observations of states in these Moiré lattices that spontaneously break the discrete translational symmetry of the Moiré lattice. So this, for instance, is work from Andrea's group from a couple of years ago, where they show that if you twist a monolayer on a bilayer of graphene by the right angle, and then put 3.5 electrons per Moiré unit cell, you can get a state that spontaneously forms a Chern 1 insulator. And the understanding from theory here is that this is the formation of a stripe density wave that doubles the unit cell area. And there's also been work in compressibility from Amir's group and probably others. All right, so what I'll tell you about are two different Moiré-based graphene systems, or graphene-based Moiré systems. Amusingly, both involve 5 layers of graphene, although I think that's a coincidence and nothing profound, in which these types of translational symmetry breaking and, in some cases, fractionalization can arise. So one by now you've heard a lot about from Long and others at the beginning of this conference, pentalayer graphene moiré with Bien. Another is a new system that we've been working on and developing in my group, which is inducing a moiré by twisting a Bernal bilayer and a Bernal trilayer of graphene by a small angle. So let me start with the pentalayer case. The device should be familiar if you've been paying attention the past few days. It's rhombohedrally stacked pentalayer graphene aligned with one Bien and misaligned from the other. And this is a measurement of the longitudinal resistance of this device, whose twist angle is about 0.9 degrees, slightly larger than the device that we heard about from Long on Tuesday. The resistance measured as a function of band filling factor and displacement field. And what I'll focus on are two distinct pockets of spontaneous Valley polarization at 0 external magnetic field that arise in this device. Both of them happen when we push charges with the displacement field to the Moiré remote layer. So if this is the aligned band, then we use the displacement field to push them to this interface. So I'll start on the electron dope side with a large displacement field, again pushing electrons away from the Moiré, and zoom into this region between the charge neutrality point and 1 electron per Moiré unit cell. Okay, so this is showing the longitudinal and Hall resistance measured with a very small out-of-plane field just to suppress random orbital magnetic switching. We can see that there's quite a lot of features, and if you have this burned into your memory by now from the past few days, I would say that overall these probably look more similar than different. We see extended insulating states at 1 electron per Moiré unit cell, and then this stripe of various types of either trivial or Chern insulators showing up from the neutrality point extending to 1 electron per Moiré unit cell. Okay, and the difference, as far as we know, is just a small change in the Moiré period. Our sample is at 10.8 nanometers, Long's is at 11.5 nanometers. If there's anything different in the microscopics beyond that, we're just not able to know what that is. All right.
Sorry, you're going too fast on me. The deep red region or very high insulating phase?
I'll talk about these one by one. Yeah. Okay, so let me try to sketch out a kind of phase diagram of the different types of behavior that we see. So we can color in purple regions whose longitudinal resistance exceeds some arbitrary value of h over e squared. So these things we can think of as trivial insulators, and those are colored in purple. And then the pink or the flesh color, whatever you like, is corresponding to regions with a zero field anomalous Hall effect that's larger than, again, some arbitrary metric of h over 2e squared. Basically just to imply a very large anomalous Hall effect at zero field.
I'm sorry, arbitrary is a factor of 10. These things are important. Factor of 10, factor of 100, mega ohm,
no.
giga ohm, I mean, how high is it?
Which one are you asking about, longitudinal or?
Both of them.
Well, okay, so you can see the color scale here is in units of h over e squared. Red is at least 3.
Okay.
Yeah, okay. All right, so let me start at 1 electron per Moiré unit cell and analyze what's happening there, and then later I'll go to fractional filling of the band. At 1 electron per Moiré unit cell, we can characterize this by, for instance, measuring the Hall resistance as we sweep the magnetic field back and forth across 0 and then subtracting the 2. This gives a measure of the anomalous Hall effect at 0 magnetic field. And if you don't like the color map, we can just take a slice at 0 field, and that's this curve. So what we see is that there's an extended range of displacement field where we have a large anomalous Hall effect, and it approaches and maybe touches h over e squared at a little narrow window of displacement field, around 0.9 volts per nanometer. And then around 0.8 volts per nanometer, it goes to 0. And even though we see an insulating state, meaning a state whose resistivity far exceeds h over e squared, over an extended range of d, the anomalous Hall effect here has vanished. So we can get more insight into the nature of these states and their topology by taking Landau fan diagrams. So the idea is to fix the displacement field and measure these longitudinal and Hall resistance as we ramp up the magnetic field. If I show you this at large displacement field where we're cutting through a very high or very large anomalous Hall region, then what we see emerging from 1 electron per Moiré unit cell is a state that looks like a Chern 1 insulator. We can determine that based on the quantization of the Hall resistance to very near h over e squared, concomitant with a vanishing of the longitudinal resistance. And also the straightest formula tells us that the slope of this state is consistent with a Chern 1 insulator. And then from there, there's an additional sequence of quantum Hall states as we dope that insulator. The situation is very different if we do the same Landau fan diagram, but at a smaller displacement field, cutting through a region where the anomalous Hall effect has vanished. There, what we see is kind of a complicated behavior at fractional band filling, which I'll tell you about later. But if we look at 1 electron per Moiré unit cell, now we see a trivial insulator. Okay, this is marked by a diverging longitudinal resistance, a sign switch in the Hall resistance abruptly across 1 electron per Moiré unit cell, and no dispersion of this insulating state as we change the magnetic field. So the Strata formula tells us that the Chern number of this state is 0. So what we can see is that there's an apparent topological phase transition in this device as we raise the displacement field. We start with the Chern 0 state at small displacement field, and then we trigger the formation of a integer quantum anomalous Hall state with Chern 1 at larger displacement field. Now, we've heard about the picture of the anomalous Hall crystal as a possible mechanism describing the formation of the Chern insulator state at 1 electron per Moiré unit cell in pentalayer graphene. And I'll go through this quickly since we've heard a number of talks about the theory of this. But the idea from my perspective is basically that if we start at a single particle level, the band is gapless as predicted by the continuum model. So when we dope to 1 electron per Moiré unit cell, we can spin valley polarize through a Stoner transition, but that's not enough to open a gap in itself. What can happen though is when we go to the full interacting limit and perform a Hartree-Fock calculation, we can see that a gap can open, and that arises as a consequence basically of taking this relatively flat spatial charge distribution and clumping it into a thing that if you took a picture of it would look like a crystal. The way that we get the Chern number is to understand basically that at a single particle level, because this band is gapless, when we integrate the Berry curvature up to the edge of the Moiré-Brillouin zone, there's no restriction on what this integral of the Berry curvature needs to be. It doesn't have to be quantized because the band is not gapless. And so we can find a situation where across a critical displacement field, at the single particle level, the integrated Berry curvature for these two different interlayer potentials is both around 0.5, but below the critical displacement field, interactions expel the Berry curvature that were in these single particle bands to form a Chern zero state. And above this critical interlayer potential, they need to pull in some additional Berry curvature from the unfilled states to get up to an integer value of 1 for the Chern number of this band. So again, once we open a gap here, the Chern number of this band, the integrated Berry curvature, has to be an integer. So somehow this has to decide whether it wants to go up or down. And so this is at least a plausible explanation for the origin of this phase transition from the Chern 0 to the Chern 1 state with displacement field. Now, there's been some ambiguity into whether this picture of the anomalous Hall crystal is really the right way to understand this physics, partially because we have to first discern whether it's not actually the standard mechanism of forming a Chern insulator in standard Moiré materials, where we can get this gap state with the non-zero Chern number just by spin valley polarizing. And there's been a lot of discussion about this. If I didn't include your work, I'm sorry about that. I didn't have space. But the idea is that even though this sort of crystal is commensurate with the Moiré, I guess the word crystal is to signify here that the Moiré is playing at most a weak role in forming this translational symmetry breaking in the limit where the Moiré is 0. Once we turn on the Moiré, we're no longer breaking a translational symmetry that's not already broken by the Moiré lattice, but nevertheless it corresponds to a large redistribution of this spatial charge density. Now, we don't have direct evidence. We would really need to take some sort of microscopic probe to this to see if this picture is happening. But one thing I can say is that if we fix the displacement field at a value that corresponds to an insulating state at nu equals 1, then what we can find is that if we go to nu equals 4, which should be fully filling the band, both the longitudinal and Hall resistance tell us that the state is metallic. So that implies that the continuum model is at least correct in predicting that there's a band overlap between the lowest Moiré conduction band and the next higher bands. And there's probably still some interactions here that play a role, but if anything, to have them close the gap would be a kind of unusual scenario. Now let's move on to fractional filling of this band. So I'm going to take a Landau fan cutting through this big pocket where the longitudinal resistance is dropping towards 0 and we have a large Hall resistance. So when we do this, the predominant feature we see here is this tilted state of vanishing longitudinal resistance and large Hall resistance. If we sit exactly at 2/3 filling and measure the Hall resistance as we sweep the field back and forth, we can see that this corresponds to an integer quantum anomalous Hall effect. We see a single sign flip between nearly plus h over e squared to minus h over e squared. And this state is extended over some range of doping away from 2/3. But clearly there's a preference for this state to want to be around 2/3 filling of the band. And so the surprise here, and as you heard from Long, is that in this sample, we see an integer quantum anomalous Hall state rather than a fractional quantum anomalous Hall state at 2/3 filling.
What is the temperature of that?
This is at a nominal mixing chamber temperature of 20 millikelvin. We're filtering as hard as we can, so it's the base of the dilution fridge. Yeah. As we heard from Yahweh earlier, there are two candidate, and also Senthil, there's two candidate states that could possibly describe this. One is the formation of a topological crystal or anomalous Hall crystal that has a √3/2 expansion of the unit cell that would basically correspond to filling one band in a reduced Brillouin zone with a Chern number of 1. There's another situation in which the crystal has a √3 expansion of the Moiré unit cell, and now you're filling two bands. The sum of their Chern numbers must be 1. And this state is related, although I'm not exactly sure it's the same as the whole crystal that Senthil was talking about yesterday. And again, we need microscopic imaging to determine what is the unit cell size and try to distinguish between these states. All right, so here's a summary of the B = 0 phase diagram with all of these factors in mind. I'm tempted to draw this diagonal line where everything below this line corresponds to a trivial insulator, something that you might imagine is basically a trivial Wigner crystal. And everything above this line is a Chern 1 insulator, something that roughly maps onto the anomalous Hall crystal. One additional thing that we can see here if we look carefully is that the Wigner crystal likes 1/3 filling. It's extended over the widest range of displacement field at 1/3. As we saw from the Landau fan at 2/3, this integer quantum anomalous Hall state is also most robust at 2/3. And then at nu = 1, this insulator is most extended over the largest range of displacement field at 1 electron per Moiré unit cell. So it's clear that these insulators at least weakly favor being at commensurate fillings of the Moiré. There's also something happening maybe at 1/2 that we don't really understand. But it's clear here that the Moiré is doing more than nothing. There's some preference for these states to be commensurate, or in some commensurate expansions of the Moiré unit cell. Okay, we can also ask what's happening as we apply magnetic field. So we can take a Landau fan diagram at this displacement field, and you might think that's going to be pretty boring because it's cutting through this just trivial insulator at 0 field. But it turns out a modest out-of-plane magnetic field can also trigger a topological phase transition. So if we apply, 2 to 4 Tesla of out-of-plane field, we kick ourselves out of the Chern 0 insulator and into a series of topological states. There's a lot of things happening, so let me call your attention first to the thing that I'll tell you to ignore for now. So there's this oval in the middle of this Landau fan diagram that seems to provide a window into some physics that's not related to anything else here. And if you look carefully, and you don't have to take my word for it, I'll show you later, there's actually quantum Hall states within this window that project to the charge neutrality point. So as I'll show you, I think this is a collapse of the crystalline order. You're just looking into some other phase. So let's forget about that. As we go to larger magnetic field and suppress this trivial Wigner crystal state, what we find now are 3 distinct Chern 1 states. So they're all parallel to each other, the same straightest slope, consistent with the Chern number of 1. They project to 1/4, 1/3, and 2/3 filling of the band. These are line slices of those data along those straighta 1 slopes. So you can see that all of these have very nicely h/e² quantized Hall resistance and suppressed or vanished longitudinal resistance. So all of these look like they're corresponding to some field-induced topological electronic crystals that spontaneously quadruple, triple the Moiré unit cell area. We can also ask what happened to fractional Chern insulators. Are they there or are they not in this sample? Well, it turns out if you look carefully, you can see signatures that indeed they are there, although not very well formed. So what we'd like to do is look within this window at finite magnetic field. We know that magnetic field suppresses the Chern 0 insulator in favor of a topological phase. So basically what it's doing is taking this diagonal line that I showed you and dragging it down to lower displacement field as we raise the magnetic field. And if we measure this same map again within this black square at 2 Tesla, by moving this Wigner crystal out of the way, we can see now this kind of sequence of topological phases. So the black arrows are denoting the straighta evolved positions of the Chern 1 states at, emerging from 1/3 and 2/3 filling of the band, projected out to 2 Tesla. And you can see that those correspond to deep minima in Rxx and near h/e² quantization in Rxy. The white arrows are showing the straighta evolved positions of the Jane sequence states up to denominator 7. Now, you may not believe just by looking at this that these actually correspond to features, but I'll show you Landau fan diagrams that I think provide a little bit more compelling evidence that they do. And just to compare once more to Long's data, basically what we're doing is looking at this region that he sees at 0 field as topological, which is unfortunately trivial in our sample at 0 field. So we're basically using the magnetic field to just peel back this trivial insulator and expose where the fractional Chern insulators were at 0 field in the slightly smaller twist angle sample. All right, so let's go back to this Landau.
So your background resistance is always very high, of the order of h over square, it seems. I mean,
Here?
well, no, in the right corner here, where you have the black arrows, for example. The back Rx is rho xx. No, the bottom, extreme bottom right corner. Rho xx seems to be.
Yeah, so in this region, that's right. In this region between the 1/3 and 2/3 topological electronic crystals, both RXY and RXX are large. But notably, RXY exceeds RXX. So that implies a big Hall angle here. You know, it's not just that RXY is large because rho XX is, you know, diverging. Okay, so let's go back to this Landau fan and look more carefully around the FCI state expected at 2/3. If you'll notice here, there's this very narrow feature where it's a little bit more red than the background. And if you take a slice, you can see that the Hall resistance actually comfortably exceeds h over e squared along this precise straightest slope corresponding to a 2/3 FCI and projecting to exactly 2/3 fan filling. So this is, I think, a clear signature of an incipient FCI state living within the sea of a Chern 1 non-fractionalized electronic crystal. If we take another Landau fan at a slightly different displacement field to get rid of this little portal and also raise the temperature, which seems to help FCI a little bit, then we can look at the straightest slopes of all of the Jane sequence states up to denominator 7. And now if you want to be generous to me, you look at this 1/3 state, you can see that it corresponds to a local dip in RXX and a very large RXY. And if I show you a slice here, you can see that rho xy is way exceeding h over e squared. Rho xx is very large, it's of order h over e squared, but again, it's smaller than rho xy. So the Hall angle, which is plotted in purple, is very large here. And in fact, if you take these slices along all of these Jane sequence states, all of them have a contiguous region of magnetic field with rho xy exceeding h over e squared and also larger than rho xx, so big Hall angle. So it seems to imply that there's some weird interweaving of these incipient Jane sequence fractional Chern insulators with the non-fractionalized Chern 1 integer quantum Hall states. All right, let me turn my attention for one slide to this very bizarre valley polarized region around 2 holes per Moiré unit cell. So we're also pointing the displacement field to push holes away from the aligned interface. If I zoom in, this is what it looks like. There's this little pocket of anomalous Hall effect. It has features that are like orbital magnets that have been seen before, where you can generate hysteretic flippings of the sign of the orbital magnet by sweeping the doping back and forth. You can also do it by sweeping the displacement field back and forth. Those are independent tuning knobs over the sign of the orbital magnet. If we take a line trace along this diagonal, you can see that there's this really bizarre sequence of oscillations, both in rho xx and rho xy. These maps are taken at 200 millitesla to suppress this random magnetic switching that happens at zero field. But if you look carefully at this probably too small image, you can see that these kind of rib-like features that show up here are really zero magnetic field features of the system. The primary state here has a rho xy consistent with a Chern number of 4. But if we take a Landau fan across that state, a naive application of the Strata formula would give you a Chern number like 7. So there's somehow a mismatch, a breakdown of the Strata formula in this case. If we take a Landau fan through these rib states, what we see is that there's a series of parallel states that all slope in a magnetic field. And again, a naive application of the Strata formula would give you somewhat of an absurd Chern number of like 13 with a bunch of these parallel states. So this is a total mystery. I mean, this looks like a series of zero field Landau levels that we don't understand at all. But again, I'll point out that this is happening at a displacement field where both the neutrality point and 4 holes per Moiré unit cell are metals. So and additional quantum oscillation measurements tell us that it seems like there are at least multiple bands, multiple Fermi pockets going on in this region. So that could explain why the Strata formula is not appropriate, since we have additional itinerant charges in the system. And it may help to explain, although I don't really know how, this very bizarre sequence of at least 11 topological states. All right, in the 5 minutes remaining, let me quickly tell you about somewhat similar physics in another Moiré system of 5 layers of graphene. Yeah, Andre?
Before you move on, to correct, these sort of 11 topological states are you sure they're incompressible?
No, I won't claim that they're not fully gapped. They're not totally incompressible.
Can you just be quantum oscillations?
They could be, but quantum oscillations of what? I mean, they show up at zero field. If you have an idea, I'd certainly like to know. All right, so here's another way to stack and twist 5 layers of graphene. So now we're taking a Bernal bilayer and twisting it on top of a Bernal trilayer by 1.5 degrees. So this is twisted ABA graphene. The continuum model from Vicious or McDonald tells us that we should have an isolated Moiré conduction band if we point the displacement field from the bilayer to the trilayer. And indeed, we see band insulators at the neutrality point in 4 electrons per Moiré unit cell. If you're familiar with the physics of twisted monobilayer or twisted double bilayer graphene, this particular sequence of symmetry broken states will look very familiar. There's a spin polarized insulator at nu equals 2. There's a correlated state at nu equals 1 that is very bizarre. So if we take a Landau fan here, what we see is that at 1 electron per Moiré unit cell, the system is a gapless metal at zero field. When we raise the magnetic field, we trigger the formation of a correlated insulator. And this looks like a Chern 0 insulator. Again, it's diverging longitudinal resistance that does not evolve, does not slope with magnetic field, and has a series of quantum Hall states projecting roughly symmetrically to the left and right. This is a bit of a mystery since Vicious or McDonald says the Valley Chern number should be 2, and if we're spin Valley polarizing, that should lead to a Chern 2 quantum Hall effect. Experiment implies Chern 0, and even with mixing of remote bands and Hartree-Fock calculations, we can't capture this, so there's something that we don't understand. But the really interesting thing happens if I zoom in on this tiny little box very near the neutrality point. There, what we see is a small region of displacement field with vanishing Rxx and h over e squared quantized Rxy. This corresponds to a perfect integer quantum anomalous Hall effect to, within instrument resolution, quantize h over e squared and 0 Rxx with a single hysteresis, single flip in the sign of rho xy from plus to minus h over e squared. And again, this is happening at 1 electron per 4 Moiré unit cells. So we're thinking about this in terms of a generalized version of the anomalous Hall crystal, where at a single particle level, the charge is modulated in real space by the Moiré eggshell potential. And interactions at 1 electron for every 4 Moiré unit cells can trigger the formation of a density wave that forms a 2x2 isotropic expansion of this unit cell. That folds the original 4-fold degenerate bands into a spin valley polarized bands with now 4 copies. And if the filled band has a Chern number of 1, then we have all the ingredients we need to explain this topological electronic crystal at 1 electron per 4 Moiré unit cells. So as a quick aside, I mean, I just want to express why I'm, framing this as a generalized version of this anomalous Hall crystal to avoid any confusion. So the Wigner and the anomalous Hall crystal are entities that break continuous translational symmetry and have Chern numbers of either 0 or not 0. There's this framework of describing generalized Wigner crystals from a few years ago in Moiré lattices of TMDs, so like WSE2, WS2 aligned, where the commensuration energy from the Moiré lattice helps these commensurate electronic crystals form. And so basically this state is the Chern non-zero version of this generalized Wigner crystal. This has very weird properties. If we take a Landau fan diagram, we see that at low field, the strata formula is consistent with the Chern number of 1 that we measure from the Hall resistivity. But then there's a first order phase transition at high field into a state that has the reverse sign of the Chern number, which tells us that somehow the state whose total magnetization is aligned with the external field has flipped its Chern number. We have some ideas for what that might be, but we don't really know. If we redo this Landau fan diagram at a slightly different displacement field, we see similar physics at low field, but then this state dies and is replaced by a different integer quantum Hall state that projects to 1/3 filling of the band and also has Chern number of -1. So basically this, quarter-filled state is killed in favor of a state that triples the area of the unit cell. In fact, those two crystals are not alone. If we raise the field to 2.5 Tesla and look over a larger range of parameter space, this region is dotted by these little regions of parameter space that have Chern 1 or -1 crystals. So 1/4, 1/3 not shown here, 1/2, 2/3, and 3/2 filling of the band. So we can take a Landau fan along this trajectory that cuts through many of these states. On this side, we see the switching of the Chern 1 to -1 at 1/4. There's a first order phase transition that kind of drifts through parameter space, and when it drifts back, it actually re-triggers the formation of the Chern 1 state going to 1/4. And then there are these additional regions of magnetic field where we have, kind of on top of the usual physics of these states, this Hofstadter states, we have these kind of scars on the Landau fan that show a crystalline state projecting to half filling, to 2/3 filling, and then another one going to 3/2 filling. And I'll point out one last feature, which is the nature of this first order phase transition that's separating these two states. And connecting it back to this little window I told you to not worry about from pentalayer graphene. It turns out that these are seemingly ubiquitous features of systems with spontaneous translational symmetry breaking of the Moiré lattice. So both in the bilayer, trilayer, and in the Moiré pentalayer graphene, we see these first order phase transitions that are hysteretic in both doping and magnetic field that show up seemingly separating states that break some form of discrete translational symmetry and those that don't. You know, the degeneracy of the quantum oscillations is the same across these transitions, so we don't think that we're changing the isospin flavor polarization. Some other symmetry must be responsible for, some other symmetry breaking must be responsible for this feature. All right, so I'll wrap up here and just say that there's, I think, a lot of open questions left to do here, but the field is, I think, in an exciting place for further exploration. Thank you.
All right, thank you, Matt. So, yeah.
Thank you for the very nice talk. I'll start with the second part of the talk, where you said, there's a switching between one and minus one. Why can't the minus one just be the time reversal partner of the plus one?
Yeah, so there's a few reasons that, of course it could be, but there are a few features that don't seem consistent with that explanation. First, it would require that the magnetization of that state would have to evolve in a kind of unusual way with out-of-plane field. It would have to have this kind of like bow tie shape that crosses through zero, which is of course possible, but not something that you generically expect to happen. The other is that these additional states, 1/3, don't have their time reverse pairs, so that's a bit strange. And they seem tied to this first order phase transition, which, as I showed in the Landau fans, seems to kind of drift randomly through parameter space. So we certainly can't rule that out, but since you asked, I'll show briefly a potential explanation that we have for this. So I apologize, I didn't talk about how this tunes with the in-plane field, which is itself very strange. But the idea is basically that you can imagine that you have two different states that are very close in energy, and that have different total magnetization associated with them. If the higher energy state has larger magnetization and a different sign of the Chern number for the valley whose magnetization is aligned with the external field, then that can trigger this first order phase transition.
Yeah, thank you for the explanation. One other question, very quick question I have is, have you done any strata sort of measurement for the crystals that you have seen in the first part? Because the line cut you cut through didn't seem to cut the 2/3.
Right. The 2/3 state is kind of broad. So I didn't show I didn't show a measurement of rho xx and rho xy along this trajectory. I mean, we could, I didn't put it in the slides. But, this line is just the line of a straight slope corresponding to a Chern 1 state. So you can judge for yourself if you think that's matching or not.
Cool, thank you.
Yeah, thanks, Matt. Very nice data. So I want to ask, just to confirm my understanding of what you said, and in terms of relationship with long pentalayer data. So I thought I heard you say that your extended integer quantum Hall state is most robust at 2/3, and not in this system, in pentalayer.
This is pentalayer.
Oh, sorry, this is pentalayer. So
I didn't call it extended, but I mean, I guess maybe I said that there was some region of doping at which you see the state, but it's really not as extended as in Long's data.
Yeah, okay.
But you can see that it is centered, the minima in RxX and the maxima, the closest to h over e squared quantization happens
Right.
precisely at 2/3.
Okay, so that's a bit different from Long's data where, as you saw, it's a wide range of doping.
That's right.
And second, in Long's data, the current that you need to get out of this integer wormhole state is smallest at 2/3 compared to neighboring
Let me show you the
densities.
measurement we did.
So it's much more fragile at 2/3 for him, but apparently not for you.
Right, okay. So this is a map of the same measurement that you're thinking from Long, where you put a tiny AC excitation and measure the differential resistance as a function of the DC current bias. So these are different XX voltage pairs and then XY. You can see that we have very similar DC current induced, for lack of a better word, like elimination of the Chern state. It doesn't have these same, critical peaks that.
No, but those peaks are not at 2/3; they are away from 2/3. That's some incommensurate.
Well, so this is the map of the data, right? So you can see that this state is most robust, very, very close to 2/3. It can survive the most DC current at 2/3 before collapsing, and then also at nu equals 1. So you basically see these features here and here that tells you that you can flow the most DC current at 2/3 and 1, and then as you dope away from that, the state will collapse with less DC current.
No, very good, thank you. This is very clear, and this is the exact opposite of what Long sees. That the critical current is smallest at 2/3 for him.
I can't comment on that. Yeah.
Yeah, so that's
that's interesting. Yeah, it's interesting.
There's
Yeah.
a difference in the data.
Yeah.
Thank you.
Did you change temperature at all? Did you go to 300 millikelvin from 20, or everything is 20 millikelvin?
No, so I switched without being totally clear about when I was doing it. All of the Landau fans I showed you, except this one, were performed
I'm more
at.
interested in zero field results. I mean, I'm already confused by D and nu. I do not want to add a B also. Just the regular data. I mean,
Right. Okay.
I'm
Look.
very
Yeah.
disturbed by
Yeah.
experimental is changing everything. It's very difficult.
No, I understand. There's a lot of
noise.
noise.
One parameter functions.
Yeah.
Three parameter, my goodness.
We do not. Okay. So let me just say that we do not see a situation in which we have a very clear cooling from a FCI state to a Chern.
Crossover that is one of the centerpieces. No, I just wanted to say the fact.
We see some things that are maybe pointing in that direction, but we just haven't. In general, that doesn't really happen here.
Let me put the question more bluntly. If Long's data did not exist, you would not see any interesting feature in this. Since Long's data exists, you can see there's some. No, these are important questions. I don't know why people.
No, I think you're right. I mean, we knew. Yeah, of course, we knew what to.
Very serious.
Yeah.
Right? So there is no feature then. Now, can you point to me where you see actual quantization? Musical 2/3 is one. Actual quantization. Something is quantized.
Are you asking only at zero field, or can I?
Of course. Yeah. No, I mean.
So.
I'm asking only at zero field.
Right.
I'm
Okay.
surprised at 4 Tesla IC quantization. Okay, in two-dimensional system.
There's two places.
Okay.
We see very close to h over e squared quantization at b equals 0 at 2/3.
That's a function of b, what you're showing.
So look at.
See something as a function of nu. That is the definition of integer quantum Hall quantization. As a function of nu.
This is as a function of nu.
That's 2/3, right? That's 2/3.
This is cutting across 2/3.
Right, but is there any other point? Now,
Yes,
I get it.
yes, indeed.
The same question.
So nu equals 1 also has.
Yeah, that's what I want. How good is it at musical 1? Do you have a line cut?
Yes.
Okay, how good is it?
It's,
Like particularly rho xx, that's what. And rho xx value, is it very small?
it's very small, but not 0.
No, but very small. Okay, good. That's good. And the last question is that I'm trying to understand, going beyond semantics. I have no problem what I call quantum anomalous Hall effect, you call topological crystal. Because our results also have the same crystal that everybody had, because you do Hartree-Fock, okay? So I have nothing against it, but I just want to make sure that when you are calling it a topological crystal, is there anything beyond the fact that you are seeing this quantum anomalous Hall, and theory says that it's a crystal there? What is the evidence? You don't see any length scale, you don't see phonons, you don't have any diffraction pattern. What is crystalline about your data?
Nothing.
Good.
So thank you for a very, very interesting talk. So I have a question about, could you comment on the relation and differences of the states with the Chern numbers plus minus one that you observe and reentrant integer quantum hole in gallium arsenide, where, for example, very large number of integer conductance states are seen between fractional states in the second Landau level?
I don't think I understood the question. Can you?
So there are a lot of reentrant integer plateaus in gallium arsenide. For example, when you are in the second Landau level, there is a whole army of them between fractional plateaus.
Yes.
So what's the relation and what are the differences in your case?
The honest answer is that I don't know. This more speculative answer is that you can construct states like this or something related. It's a whole crystal state that Sento was talking about that are the spiritual analogs of the reentrant integer quantum Hall in partially filled Landau levels. But it goes beyond what I can say from experiment.
Okay, thank you.
Yeah.
Thanks for a very interesting talk with many, many phenomena that should give us food for thought for theorists. I wanted to ask a question about a more trivial feature here. Low doping, you were using the word Wigner crystal. Could you comment on why, what non-trivial features show it to be a Wigner crystal, if any, yet?
I think the most compelling thing that I see here, and admittedly it's circumstantial, but you see that this insulator is the most extended in displacement field at 1/3 filling, which is a suspiciously commensurate filling of the Moiré unit cell. So indeed, without imaging, we have no way for now to distinguish between some disorder localized insulator or something with true long-range order. I don't know. There are measurements that could be done to try to suss this out, both imaging and other maybe like RF measurements, but we haven't done them yet.
Thank you.
Thank you, Matt. Maybe I missed it, but for this strata formula slope that you mentioned here, did you actually can tell whether it's a anomalous Hall crystal at nu equals 1 plus a whole crystal, or it's an anomalous Hall crystal?
This?
Yeah.
No, we can't distinguish from
You
just
can-
this transport. Both of them.
I thought Senso's talk told us that you can tell if you see a strata formula.
As far as I understand, and Sento can correct me if I'm wrong, both of these states are gap states with a total Chern number of the filled bands of 1.
Oh, okay.
And so they both show up as a Chern 1 integer quantum anomalous Hall effect.
I see. So there's no experimental
Well, you can ask Sento what experiments, but I mean, imaging would be the most direct. I think the prediction is that these have different areas of the unit cell.
Okay.
Whether there's a non-imaging experiment that could distinguish, I don't know. Okay, so we measure the phonon spectrum. We just have to measure the phonon spectrum of the crystal.
Going back to so if you go away from 1/3 at some incommensurate filling, so then it's there's a question of whether it's just a localized insulator or a pinned crystal. Pinned crystal will have collective motion, right? Sliding, deepening. So do you see nonlinear? What's the IV curve look like?
Okay, unfortunately, I don't have it here. When you look at 1/2, there's a sharp nonlinearity.
Yeah, but in the alleged Wigner crystal, to answer Dan Parker's question.
I don't have the data in the slides.
But you have seen nonlinear. You've seen deepening, collective motion of the.
I just can't remember if we've extended this beyond 1/3.
Okay.
I mean, within this insulating regime that's connected to the one at 1/3, you see sharp nonlinearities in the insulator. So my suspicion is that if we had just extended it to 1/3, we would also see that. But I don't have it here, so unfortunately I can't tell you.
Okay, so it's clear a lot of people are interested, but I'm afraid we have to move on to the next speaker. So let's thank the speaker again.